Yesterday we looked at polynomial theorems. Today we're going to look at some polynomial results. Okay. So this first one here, what are we saying? If we know a polynomial has k distinct, that just means different, zeros, we'll just call them a1, a2, a3 up to ak, then it must be able to be factorised as x minus a1, x minus a2, x minus a3. In other words, there'll be a linear factor for each one of those solutions. We know that via the factor theorem. So we've got a quartic, and we're told that 1 and negative 2 are zeros or solutions to this polynomial. So let's show that. Sub 1 in, we get 0. Now look, when you're asked to show it, don't just write polynomial 1 equals 0. You view it works. Show the substitution step, okay? Polynomial negative 2 also turns out to be 0. So we know, yes, by our factor theorem, 1 and negative 2 are zeros or solutions to that equation. Thus, x minus 1 times x minus 2 must be a factor of this polynomial. Hence, go and factorise it. All right, there's the polynomial. I've expanded out the x minus 1 times the x plus 2. So we know x squared plus x minus 2 is a factor. And then I can get the other one. If you want to use polynomial division, you can use polynomial division. Or we, once again, can just use some logic here. Leading term times leading term. So x squared times something will give us x to the power of 4. Well, that's got to be x squared. Now let's have a look at the constant. Negative 2 times something will give us negative 10. Well, that's got to be plus 5. We need the middle term. Oh, let's have a look at the x's. If I was to expand this out now, how many x's would I have? 5. How many do I need? So that must be it. We must be done. There mustn't be a middle term for that one. And again, if you're unsure, check one of the other ones. If I was to expand that out, how many x cubed would we get? 1. And that's what we want, so that works. All right, well, let's do the x squared as well. Let's just make sure of it. How many x squared at this stage? And it works as well. So it confirms. So yeah, that must be the other factor. So now I'll refactorise that first quadratic. X squared plus 5, of course, doesn't factorise. Well, not with real numbers anyway. That brings us on to the next idea then. So if the polynomial, degree n, and we know all n of the zeros, so this time I'll call them a1, a2, a3, all the way up to an. Well, if I've got all of the zeros, I've got the polynomial. It must factorise down to be x minus a1, x minus a2, x minus a3, all the way up to x minus an. Or okay, it could be some constant multiple times that. But that basically is the polynomial we're looking for. A polynomial of degree n can't have more than n zeros. Because if it did, then when you expanded it out, you'd have this extra factor. And the power would get too big. We've got to stop at x to the power of n. Let's try this one. Polynomial has a double zero at negative 7, a single zero at 2. Write down a possible polynomial. What they're getting at here is a general one that would cover every possible solution. So what do I know? I know x minus 2 is a factor. I know x plus 7 squared is a factor because it was a double zero. It could be times some other polynomial. But that other polynomial can't have a 0 at 2 or negative 7. Because if it did, well, say it had another one at 2, it would no longer be a single 0 at 2. Because if there was another one with 2 as well, it would become a double one. So it's any possible polynomial, but that possible polynomial can't have 2 or negative 7. I suppose, again, I could multiply it all by some constant number. What about if it was monic of degree 3? So let's write in what we know, but I can't do much more because that is already of degree 3, and monic means if I expand it out, it's got to be x cubed, which is what it is at this stage. So there's nothing more to do to that one. There is only one possibility, and that's it. Monic of degree 4. Okay, again, that's what we're starting with, but that's degree 3 at this stage. So if I want to make it degree 4, I'll multiply it by another linear factor. But a can't be 2 or negative 7, because then that would change the single root into a double root, or the double root into a triple root, and so on. A polynomial of degree 5. X minus 2 times x plus 7. That's of degree 3. I want to make it of degree 2. I'm just going to say times qx, which is a polynomial of degree 2. But it does not have a 0 at 2 or negative 7. Could, of course, be some multiple. They didn't say monic in this case. So it could be some multiple of that as well. Now I'm going to contradict myself. Remember we said a polynomial of degree n can't have more than n zeros. So now I'm saying, well, if it does have more, then what do we got? We've got to have the 0 polynomial. The 0 polynomial is a very strange polynomial. It's just 0. How many solutions does that have? Put it this way, if I said the polynomial was x minus 2, how many solutions would that have if we were trying to find the x-intercepts? Yeah, it'd just be x equals 2. It just has one solution. If I wanted to make 0 equal to 0, how many solutions do I have? Oh, someone said 1. Someone said 0. Someone said infinite. It's actually infinite. X could be anything you like, because there's no x in my equation. So I can make x, so it has an infinite number, which means its degree is n, because its degree could be anything. It's weird. 0 is just a strange number. Okay, whoops. So if you ever see a question which simply says, it'll just say something like this. Polynomial ax cubed plus bx plus c has 5 zeros. What's the polynomial? What's the value of a, b and c? Well, the value for a, b and c must be 0, because the only way it could have more solutions than the power is if every coefficient was 0. That's basically the sort of thing they might ask. All right, number 5. If polynomial x is congruent to qx, congruence, I know we normally see it in geometry. All congruent means is identical in every possible way. Then the coefficients of each term must be equal, because they're equal in every possible way. So if I have the polynomial on the left is congruent to the polynomial on the right, then the only conclusion that I could draw is that, well, A1 must equal A2, B1 must equal B2, C1 must equal C2. All the coefficients must be equal because they are identical in every possible way. Whoop. There we go. That'll do us for today.